is Sebastian.
And I'm Chris Mudnitsky with the Fort Worth Astronomical Society, and we're going to be doing a virtual star party today, live. We'll be looking at the winter sky, doing some imaging, doing some observation, and talking about astronomy and talking about astronomical imaging. So somebody is ready to go to bed? No? I'm sorry, but it's time. Ready? I know he wants to stay around for later, but it's going to get late, and we have things to do. All right. So Sebush, it's time to go. Okay. Bye bye. He's not really crying. Sebush, can you close the door, please? Again, my name is Chris Wojnicki with the Fort Worth Astronomical Society, and we're broadcasting live from Fort Worth. Actually, I'm in Burleson right now. This is just south of Fort Worth. Um, I am currently in my studio. I am not outside with my telescope because I have made everything remote. I am now able to connect remotely to a computer outside, which is connected to a telescope, which is connected to, which has cameras on it, so that I can do all the imaging right here where it's nice and warm and I don't have to freeze anymore. That was one of the biggest issues that I always had about doing winter star parties and even summer star parties. Is I had to be outside with the equipment right next to the telescope. And when I was, it could be very cold. Some winters, it got down well below freezing. So those are not fun to be outside because you're not moving. You have to sit down in front of the computer the entire time. In the summer, we had to deal with high humidity, high temperatures, and bugs. Lots and lots of bugs. When you have computer monitors that are shining at night, um, insects love to congregate on those. So I would constantly have to sweep off bugs off my keyboard, off the monitors. It just wasn't very much fun. So now I will be able to do more remote imaging with the Fort Worth Astronomical Society. We actually have our dark sky site. This is located about call just over 2 hours west of Fort Worth. Um, it's on about 5 acres. We have a number of telescopes out there already. We have a number of Dobsonians, and we have a few refractors, and I believe we have the Celestron 11-inch scope out there as well. So if you join the club, you can go to fortworthastro.com, fortworthastro.org. You can go to our Facebook site, and you will be able to join the club and use our equipment. So you don't have to own a telescope. You don't have to have uh, gear of your own. You can actually just use ours. You can go out there, use what we have. We have eyepieces as well. We have star charts. You'll be able to start observing your first night out there. Our club meetings are the third Tuesday of the month at 7 p.m. at the University of North Texas Health Sciences Center off of, it's between Montgomery and University on Camp Bowie. And we're in room 100. So there's a map on the website on where to go to. Again, with the Fort Worth Astronomical Society, we do provide a lot of the equipment. We do have a lot of benefit if you wish to join the club. One of the benefits is actually doing things like this, doing these live streams and being able to watch and ideally participate. So, is the audio quiet? It may be a little bit quiet. I think I have it turned up as high as it's going to go. Let me see if I can push this a little bit higher. But it is a little bit quiet. Growing pains with the studio. I've got to do some setups. It's a little bit different than I'm used to. Let me see if I can bring this. This should be quite a bit louder. I believe I'm clipping now. Okay. That should be significantly better. Okay. Audio is fine. YouTube on our smart TV. Cool. All right. And this is kind of an impromptu start party. So I didn't plan this well ahead of time. It was more of the weather is fine. The weather will only be fine for a very small window. And this weekend, it will be cloudy. So we have a new moon right now. We're close enough to a new moon. The moon is actually almost setting right now, so we're not going to be able to see it. It is behind my house. So we'll be doing stuff other than the moon. Right now, I have a laptop over here that I can uh, I can go ahead and watch chats. So if you have any questions, comments, concerns, I can go ahead and read them and respond just right away. And then I am connected already to uh, one of the telescope, or the telescope that I have down there, so we can start doing stuff. I also was able to do some imaging last night. So we're going to go through the process of what we need to do. First, I'm going to show you what is out there. So I need to bring this up in just a moment, and I will have I actually went out today and looked at some. All right, let me rephrase that. I went outside today with the telescope already set up. I set this up last night. I was able to do some imaging. So today I went outside just so I can take some pictures so I can show you the setup. And this, let's see, let's go ahead and switch over. So there we go. So there is the setup. This is a Celestron 11-inch Schmidt Cassegrain. It is an Edge HD. This is the newer optic set. What you're seeing right now is the telescope and a big old dew shield, which keeps the dew off, and it was very, very important last night. And I have a guide scope. Right here is a little polar scope. This is called a PoleMaster. This lets me do a polar alignment very, very quickly. And this is the CEM60 EC mount, the Ioptron CEM60. From the back, you notice that I have a focuser attached, the remote robotic focuser, and I've got the camera on the guide scope, but there's no camera here. Typically, you would have either an eyepiece on the back, a little diagonal in an eyepiece, or you would have a camera on the back. I don't have that. The camera is actually in front, and I don't have a picture of that. But what I can do with this, there's actually a lens assembly up in front called a Hyperstar, made by Starizona. The Hyperstar lets me put the camera at the front of the telescope. This lets me take it from an f10, which is a very slow telescope, to an f2, which is a very fast telescope. So someone here is going to have to learn how to use some of this equipment not too long from now. I bet. Okay, so right now, do you have a question?
Yeah.
Uh-huh. What's your question?
How long is this gonna be?
As long as we can. As long as
We can make it.
As long as we can make it. I plan probably to be done around 10 o'clock, maybe 11 o'clock at the latest. But we'll see. The cloud should be rolling in about 12 tonight, so we shall see.
Oh,
It won't go any further than that.
Poopy poo.
Sebush, now you can go to bed.
Yay! No, yay.
Okay, so go to bed. He has not been going to school this week because it is the holiday, and therefore he has been staying up way too long, well past his bedtime. We'll fix that next week. Okay, what are we looking at right now? We are looking at the live view from the telescope. What do we see? Not much, a couple of dots. That's all we can see. One of the neat things we can do is something called plate solving. So a plate solve is basically we're taking a picture of whatever we're looking at, and the computer is now comparing it to its map of the night sky. What is it actually looking at? In this case, we're looking at Calf, which is a star in Cassiopeia. Why are we looking at that? Because I was focusing on that. I was doing a remote focus so I can make sure my stars at this moment are sharp. We have to focus several times through the night because the temperature through the night is dropping. As it drops, what happens to materials? They contract, they get a little bit smaller. So our telescope itself gets slightly smaller. And because we're dealing on the scale of micrometers for our focus, just the temperature changes get our telescope out of focus. So every hour or so, we have to go through with the routine, refocus, make sure everything is nice and sharp, and then go on. I didn't do that last night. I focused at the beginning of the night. And I thought, okay, well, this will be fine. But then as the night progressed, my images got more and more out of focus. And when I looked at them, I realized, okay, they're not small pinpoints of stars. They're now out of focus little blobs. You could still see an image, but without a tight focus, it wasn't nearly as sharp as it could have been. Oh boy, I need to keep this thing going. The laptop on this side, because if I don't, it'll go ahead and lock up, which is fine. Not a big deal. All right, so Chris H., pleasure to meet people at the planet viewing at the Bedford YMCA. Yes, that was on Saturday. I was out there as well. I was not really on camera. Our Bob Circus was on there, so yes, excellent. It is a very, very nice place. It is in the city, so the skies aren't too dark, but the YMCA is really nice to us and lets us do a lot of star parties out there. We also have a number of public star parties. Not during the winter, I don't believe, but we do Dinosaur Valley State Park in Glen Rose, Texas. It's about an hour's drive from Fort Worth. They have a really nice place for us. It's their overflow parking, but we go there, we set up, and we do imaging. We do electronically assisted astronomy, which is what we're doing right here. And this lets us show the night sky to the general public. So you can come out, look through telescopes with eyepieces, see things with your own eyes, or you can see on computer screens what we can do with imaging. When you take a regular photograph of whatever, you take a picture of your cat, your dog, your car, take a nice panorama while you're on vacation, take a selfie. When you take those images, you take one picture. Usually. Sometimes you may take 3 or 4 or 5, but then you pick the best one out of them. But it's still just one picture. With astronomy, we don't do that. We take a lot of pictures, sometimes hundreds of pictures. And the reason is, one picture, we're not taking it for example on here. This is 250 milliseconds to get this picture. That's not much there. It's a couple of dots. But if I change, actually, let's do this. So here's the raw image. That should be the raw image. There we go. The raw image. So we have calf somewhere here. Let's zoom in on calf. Well, there we go. I'm going to get rid of my deep sky annotation temporarily. That's calf right there. Does that look good? I don't think that looks very good. I don't think this is a good exposure. I think we have to do a refocus. I don't think this is right. Whoops. I don't want 30 seconds. I want 1 second. 1 second exposure should be a little bit brighter, but not by too much. And we're going to play with the histogram. There we go. Okay, that's not in focus. That's not really in focus, so let's fix that. Oh boy. Let's go. Let's see what happens. So what I'm trying to do is get this thing down to the smallest point possible. I think my collimation is a little bit off as well, because it's not only is it not round, but it's actually kind of bright on one side and dim on the other. It should be bright all the way around. For tonight, let's not worry too much about it. And what I'm doing right now is I'm stepping my motor, and I'm seeing if this gets bigger, if this gets smaller. And I think it's getting, well, let's see. Let's keep going, because I thought I had a decent focus, but apparently I don't. And the only thing I'm really worried about is getting something clear. So we have to do the, oh, there we go. Now it's getting a little bit better. It doesn't need to be totally perfect, not for tonight. I'm not really worried about perfection. All I'm worried about is getting this a little bit tighter than what it is. And yeah, it's hard to say, isn't it? Is it getting bigger? Is it getting smaller? And what I could do this. let's see if we can get this a little bit faster for processing. I can actually shrink this down and say, hey, don't use the whole sensor, just use part of the sensor, just the very, very center of it, because I want this to go fast. Okay, there we go. So again, we want this to go a lot faster processing, and we're doing 1 second exposures. So let's see what this does. And honestly, when we were doing the testing on Saturday night, we were connecting to a remote telescope at our dark sky site. And it was not ideal in the beginning. We didn't really have the proper procedure on how to turn it on, how to turn it off. And this is now getting bigger. So I'm going to go like this. I'm going to go 1270 and see what happens. So now this is going to move the focuser to a new position. We're going to see this thing hopefully shrink down. And there is another method to do it, but I have to be down there to do it. I have to be outside. And I'm not ready to go outside and leave everybody hanging here. Whoa, there we go. This is significantly smaller. Okay, so let's go positive direction a little bit more. So we're going in the wrong direction beforehand. All right, hey, got Naz from Astronomy on. This is the boring bit, so welcome. All right, I think it's getting a little bit bigger now. Maybe? Oh, no, there it goes. There it goes. Now it's smaller. All right, let's go a little bit. Keep moving a little bit. Did you come back when you should be in bed? Okay. Okay.
Fine.
All right. So here we go. So now this is getting a little bit tighter. We're almost there. Once we get down, this is probably good enough for today. Let's get a little bit tighter. But now we have a number, 12,870. Okay. 12,970, about 13, roughly 13. This is not bad. Okay, this is not bad. Let's go ahead and call this close enough in focus that we can go on. All right, so we have something. Let's zoom back out, and we don't have much. Happy New Year. All right, we're going to do a full screen, auto zoom, and the software is called SharpCat Pro. This is really nice setup for imaging. Shouldn't you be in bed? Did you brush your teeth yet?
No.
Go brush your teeth. Go brush your teeth. Close the door.
I'm going to mommy.
So we are doing a 1 second exposure right now of cat. We can't see much, especially because I don't have the histogram stretched. What we're seeing is raw data. This is exactly what the camera is getting. There's not much here. So we have to do a couple things. One, just stretch the histogram and see what happens. Do we see much? Hey, we see a bunch more stars. Okay, more stars have popped up. Great, fantastic. But that's not enough. A 1 second exposure is not nearly enough to get good data. So what do? Well, get a longer exposure. So let's do 30 seconds. What are we going to see with a 30-second exposure? Turn that down. Okay. I know. Move over. This is mine. Move. So we are 14 seconds in, 15 seconds.
This is a bit backward.
Yes. What you've noticed is that there is a delay with YouTube. It's about 30 seconds from when I speak until when it's actually streamed out. That's just a function of the way YouTube works. Hey, cool. Now we got something. So with 30 seconds of exposure, we can see a lot more. Not only can we see a lot more, but now I can fix the histogram. And now we have a lot more stars. We're able to actually see something. The scope is currently tracking, but it's not guiding. And we'll get into that in just a little bit. But here we go. So we're able to see stars. And if I zoom in, that's not too bad. Okay. Not too bad at all. I'm able to see, it's not perfect focus. It's fine. I'm not worried about it for tonight. But we are able to see a lot of stars. We're able to see a lot of really dim stars as well. What the histogram stretch does is it basically says, okay, take your dark, anything dark, and then bring up the levels until it's much, much brighter. And when we do that, we see all this stuff in the background here. This is all noise. This is all heat noise. And this is one of the reasons why we take a bunch of images. Why do we do it? To average out the heat noise. We do something called stacking. You take dozens to hundreds of images and you layer them up and you align them. And once they're all aligned, you add up all the pixels per column and row in 3 dimensions, essentially, and then you take an average. And anything that's bright, stars, nebula, galaxies, all that stuff will average out to a higher signal level than your noise. Your noise will tend to average out to a much lower level. So you smooth out your noise and you increase your signal. Okay, this is the signal to noise ratio. And it turns out for every time you double the number of images that you take, you have your noise floor, essentially, which is really, really cool. You can take hundreds and hundreds of images and decrease your average noise by a lot. With this camera, if you look right down here, I have a cooler on it. See, can you see that? Yep. So there's a cooler. The cooler actually lets me cool down the chip. So right now the chip is at minus 23.4 degrees Celsius. My target is minus 25. But the cooler is going 100% right now. This is a Peltier cooler. This is a thermoelectric coupler. And the way it works is there's a hot side and a cold side. And when you run a DC current through it, well, sorry, let me rephrase that. There's 2 sides to it. If you run a DC current through it, it creates a hot side and a cold side. You put the cold side right up against the sensor, and on the hot side, you put a heat sink and a fan to dissipate the heat, to take it away. Otherwise, it will burn out. The cold side can get very cold. In this case, this can get 35 degrees below ambient Celsius. 35 degrees Celsius below ambient. And what happens when you decrease the temperature of the sensor? You decrease the amount of heat noise on it. So every sensor is going to get some noise from infrared radiation from within the camera. Even if I cover it up completely, I can cover it, put it in a black bag, and leave it in there and take pictures, and I will still get noise. It's just infrared noise from the operation of the camera, from all the environment around it. By using a cooler, I can decrease all that. So this is kind of cool, but honestly, there's not much to see. This is just 1 star in Cassiopeia. So let's see what we can see. And I'm going to jump onto here, which is my control program, and this is Starry Night Pro. I can do a lot of cool stuff. So what we're going to do, what's a good thing to look at? Oh, we got a satellite going through, at least, well, it says it's a satellite. This could be space junk. Space junk is considered a satellite as well. And yesterday I was imaging the California nebula, so we can go to that, but not quite this moment. First, I want to get to Pac-Man Nebula. Pac-Man Nebula, here we go. I'm going to come over here, and we are close by. Cool. So we got that, and we can right-click, slew to the Pac-Man Nebula. So it's moving. It's almost there. Almost there. And here I'm going to come in and change it to 4 seconds. So do a 4-second exposure. Now we have all these streaks from the data. Can take another image. And now we have a different star field. What are we looking at? I don't know. I do not have the entire night sky memorized on this level. So we use a plate solve. Hey, cool. We're pretty close to it. Excellent. So we have IC0011, which is the alternate name for it. And this is also NGC 0281. NGC is the new general catalog. IC is, I don't remember, it's some other catalog name. So let's do this. We'll just center it into view. And it'll move just slightly. I didn't really need to center it, but it's fine. And we're going to shut that down. We're going to come back and do a 30-second exposure and see what we can see. So again, this is one quick image, and then we can do some live stacking and see what's out here. So the Pac-Man Nebula is a region of ionized hydrogen gas. There are stars within the region, and this because this is a star-forming nebula, and the young ones, the big ones, the big blue bright ones, they throw off a lot of their energy in the ultraviolet. When they do, they cause the gas to glow. There we go. Now we have a Pac-Man. And it's called the Pac-Man because in some orientation, here's the mouth, here's the body. And let's play with the histogram some. This is the raw data. Again, I got like a dot here, dot there, a dot there. There are a couple stars in the field, but when we stretch the histogram, hey, now we have something. Cool, let's zoom in on that. All right, so this is just a 30-second exposure. If I increase the time, I get better data. I get more data. So increasing the time to 1 minute. See what happens. Do a 1 minute exposure. While I do that, I will do a live stack. Let's do that. Let's see what happens with the live stack. Let's see what I have on here. Oh, I want my noise. Let's do, what do I have for my, oh, I did do a, ooh, that's fine. I did not do a 60-second dark frame. Oh well, I have a 2-minute dark frame, I have a 3-minute dark frame, and a 4-minute dark frame. And when I was talking about taking the camera and putting it in a black bag and doing imaging and seeing all that noise, that's actually what we do. We take the camera, we cover it up completely, and then we take an image for with our whatever settings we want for a length of time, and we take a number of those images and we stack those images, and we call that our dark frame. And the dark frame is essentially, let's fix that. That's not what I want to see. The dark frame is essentially the noise of our camera at the heat level that we're at. Why is this not working? I have not done this very well before, so bear with me. If anyone's got ideas, go ahead and let me know, because I don't remember how to do this. Do the live stacking. There's a status, the histogram, stacking itself. Sure. It has been a while since I had to do this. So let's look at the histogram. Let's wait for the next one to come in and see what it says. Is it better? It ain't any better. Yeah, total exposure. I don't think this looks right. No, this does not look right. Anything? I'm not seeing enough data on here. Yeah. Ah, there we go. Ooh. That's not, that doesn't look that great. There we go. That's somewhat better. Okay. Yeah, I'm not thrilled with this live stacking. That's why I do processing. And I did my, I took my flats this afternoon. And funny enough about taking flats, so we take these pre and post images in order to help process our images. We take the darks to get our, like the base brightness, we take our darks to get the heat noise out of our images. Okay, so we can subtract the dark frames. Then there's stuff called bias frames, and the bias is we just take images as fast as possible with the camera. and that's the camera's itself base noise level, which is fine. So we subtract the dark frames, we subtract our bias frames. And then we have to worry about vignetting. And vignetting is when you take an image and the sensor is just a little bit too dark for the image circle that your optics provide. And you can sometimes see this with cameras that you may have put like a really wide lens on. And the vignetting is that the edge of your image is darker than the center. You have a bright center and it kind of darkens as it goes to the edge. So we see that in telescope optics as well. And the way we get rid of that is we take a flat. And a flat is when you point your optics exactly as they are, your entire optical train. You don't move your camera, you don't do anything. You point it up at the sky and you put like a white t-shirt over the end and you stretch it out, or use a flat white panel to do this. And you take those images, I take like, I don't know, 50, 100, however many you need, and you stack those, and that gives you your flat. So this says, no matter what, this is how we're going to remove the vignetting from your optics. Again, fantastic, neat trick to do. I forgot when I was doing my flats that that my whole telescope was pointed at the North Celestial Pole near Polaris. And so I took my flats, and this is in the afternoon. This is about 4:30 in the afternoon. I took a quick break, went outside, started this thing running, and when I did, I looked at my flats, and then I put the flat here, apply the flat, and then I kept on imaging. I noticed there was a dot there. There was a black dot with a white dot next to it. I kept looking at it, and I kept looking at it. And I realized, oh, I actually had Polaris in my field of view. I was able to see Polaris during the day with the telescope. And instead of getting a region with no stars, I had Polaris right there. And now I have a black spot in my flat, which is being subtracted from the image I was taking. No good. I had to redo all my flats. So now we have a little bit of inverse vignetting, darker in the middle here and brighter toward the edge. I'm not terribly worried. We can always fix that in post. But we're seeing the Pac-Man. Let's zoom in on that. So we have a bunch of stars, and right here in the middle is the cluster that is throwing off all the ultraviolet. And still pretty noisy. I mean, this is a 1 minute exposure. The temperature is down quite a bit, but it's still a fairly noisy one. And we've only been exposing, it's 6 frames, total exposure 6 minutes. That is not a lot. But at least it's something. So I can actually darken this up. Whoops, don't want to do that. Don't want to do it this way. There we go. So we can take that noise that we see and kind of bring it down a little bit. Now we can see some additional detail through here. So what do we see? We see the cluster in the middle that's throwing off all the ultraviolet radiation. We can see the hydrogen gas all around. We see this little bubble nodule of hydrogen with a little shadow. We see these darker spots through here. I'm not 100% positive, but usually if you see isolated black blobs like this within a star-forming nebula, we call these Bok globules, B-O-K. And these are regions of active star formation. There's usually a star right there in the middle of it. And it's a protostar. It's just forming. It's still collapsing. And it hasn't gotten to the point yet where it's fusing and pushing, or let me rephrase that, it hasn't gotten to the part of its life when it is fusing and has pushed out all the dust from the local vicinity. All these other stars around here, they've been fusing for long enough that they pushed all the dust out, all the dust and gas, and now they're visible. A brand new star is just going to start pushing that out, and I believe it's called Pyeongtaang radiation. Pointang radiation, something like that, where the light pressure from the star pushes dust out from the general vicinity. We have that with the sun as well, with our sun. So the larger dark bands like this, anything that you see that's dark is dust that is blocking the light from behind it. So the nebula is this, it's the bright area, but the nebula is also the dark area. So we have bright nebula, or emission nebula, or reflection nebula, and then we have dark nebula. Excuse me, and the dark nebula it's just dark. It's dark because it is blocking the light from behind it. Nothing is exciting it, it's just dust. Nothing is necessarily reflecting off of it, so it blocks the light from behind. And I'm going to see maybe we can catch something over here. If it's here, if it's within the field of view. I don't see it. I don't see it. I am looking for something called Able 2. Where is Able 2? And it should be here. I know. Wait, hold on. That's it right there. That looks like it's it right there. This looks like it's in the right position. See if there's anything. There's nothing else that I can see that would be it. This looks like it's just right. How do I know this? Because I've imaged this thing before, and it just so happens to be in the right position, right across over here. I haven't memorized it. It's just I imaged it earlier. So, an Able 2, if this is another catalog. Here we go. That little thing right there is a planetary nebula. It is small. It is dim. Here it looks like a star. But Able 2 is a planetary nebula. This is they're called planetary nebula because through the telescope they looked like little disks, little planets. They didn't look like stars. So they were called planetary nebula, even though they didn't really look like planets. They didn't move anywhere. They were disc-like, not point-like, like all the stars you could see through the telescope. So a planetary nebula is when a star, like our sun, gets to the end of its lifetime and it stops fusing hydrogen and starts fusing helium. And when it does, when it stops fusing the hydrogen, the star actually collapses. So a star is a balance between the outward pressure of the fusion reaction trying to blow the star apart and gravity trying to collapse it down. So when it stops fusing hydrogen, the star collapses. When it does that, the temperature in the core and the pressure in the core rise high enough that now helium fuses. Once helium starts to fuse, it gives off a lot of energy and pushes the star back out. In fact, it pushes it so far out that it can blow off the outer layers. When those outer layers are blown off, they create a planetary nebula. These gases go away from the star, and now the star keeps pulsing again. So once it's done with the helium, it starts fusing. It goes through lithium, carbon, oxygen, usually down to carbon. It all depends on the mass of the star where it stops fusing. But those gases get pushed out. So when we see greenish blue, like that one right there, this is an indication of oxygen. That oxygen is being excited. And when the star is pretty much dead, all that's left is its core. The core is not fusing. It is just glowing from residual heat, tens of millions of degrees, usually about 10 to 20 million degrees, white hot, and it is slowly cooling down, and it can take billions of years to cool down. In the meantime, it's throwing off a lot of ultraviolet radiation, and that is causing all those gases to fluoresce. So we have planetary nebula, which have hydrogen in the outer shells, and that glows red. And then something like this, like Able 2, we are picking up the blue-green color from oxygen. So it is small, and it is very distant, but I was able to pick this thing up, and I was pretty happy that I could. Now we have a question is, why are the stars different colors? Stars are not white. Our sun is white, at least to our eyes. That's why our lights, when we say daylight, we say 5,600 kelvins, which is roughly the temperature of the surface of the sun. So the sun is white, but we classify it as a yellow dwarf based on how the light, um, basically the light from the sun in the spectrum. So the cooler the star is, actually, let's go back. The smaller the star is, the cooler it's going to be. And it's all because of gravity. So the small stars, M-class stars, red dwarfs, are very, very small, but they can last for hundreds of billions to possibly trillions of years. They very, very slowly fuse their hydrogen over a long period of time. They're very, very cool, less than 3,000 degrees, 3,000 kelvins on the surface. They're very, very cool, dim stars. And they're very small as well. But they tend to be very active in like solar flares, so it might be difficult to find life around M-class stars. As you get bigger to our star, like a G-class, they're bigger, they're brighter, they throw off more of their energy, not in the infrared and red part of the spectrum, but toward what we consider the visible part of the spectrum. And our star should last, it's lasted 5 billion years. It should last about another 5 billion before it becomes a red dwarf when it stops, or sorry, a red giant when it stops fusing hydrogen. Bigger stars, they're white, like Sirius, and then the very biggest stars are blue-white. They're very, very large. They only last for a couple million years, and then they explode in supernova. So here we see red stars, there are some yellow stars through here, and white stars, blue stars. Now we're seeing lots of different colors, and these are actually the colors of the star. Let's zoom out again, auto. So here we have the Pac-Man Nebula. I'm going to zoom into something a little bit more. Let's see, 75%, so we can see more of it. Okay, so we've taken 15 images over 15 minutes, about to be 16 in a couple more seconds, and we've cleaned up the noise quite a bit. So I'm going to zoom in right here. This isn't bad. This is not bad. We've cleaned up the noise quite a bit. So the more images you take, the lower your noise floor can be. With the stacking technique, we're just getting more and more data. So these are actually coming in clearer now than they did before. So we can see this little protrusion here comes out a lot clearer. These Bach globules are a little bit clearer as well. It's not perfect focus. It's fine. It's fine for tonight. I'm pretty happy with this. So we're able to see a little bit more detail. There's a little bit of dark area right here. Going up, there's another Bach globule up here, and we can see the nebulous fading out. So that's pretty cool. This is the Pac-Man Nebula, and we're going to do a quick plate solve. And it says, hey, let's take a look at this image. Here's where we're pointed at. Where exactly are we pointed? What our focal length is. So this is 540 millimeters. This is effectively 540 millimeters because this is an 11-inch telescope at f1.9. So it's very big and very fast. Let's go ahead and 17. All right, let's just finish up one more. We'll do 18 images out of this thing, and then we can jump on to the next one. If you have any suggestions of targets that you want to see, wider field is better. If it's really, really tiny, it'll be really hard to see. For example, looking at the planets, we can try, but this is not a long focal length telescope in this configuration. If I was going to be doing the moon, if I was going to be doing the planets today, then we may actually do that, not tonight, in 2 weeks. Well, no, in a week. We'll see. We'll see what the weather is next week. But I can go from the hyperstar assembly in front of the telescope and just put the camera in the back in its normal assembly. And then I can be either f7 or f10, depending if I use a focal reducer. And then we can actually start to see a lot of detail. We can do planetary imaging, and planetary imaging is much different than what we're doing today. That involves lots and lots and lots and lots and lots and lots of pictures, tens of thousands to possibly hundreds of thousands of frames, and then picking like the best 1 or 2% and then stacking those. It's another process, but it's cool. We can do it. What are we doing right now? So let's give 15 more seconds, 18 images. All right, 15 more seconds, then we can stop this live stack. I'm saving my raw frames. I'm getting them. Cool. All right, let's do it. So I'm going to go ahead and stop it, stop that live stack. And then we're back to raw data. This is, or almost raw data. Okay, so I'm saving my stack. Cool, 16-bit. Love this camera. Does really, really good work. You can see I had a little bit of drift because it's black band. It's fine, we're good. So I'm going to go down to 4 seconds again because I need to be able to do a quick plate solve on wherever we're going to go. So what's our next target? And we are here. Here's the Pac-Man Nebula. This is up near Cassiopeia. So we could do the heart and soul. That is totally feasible. Everyone likes to do those. I'm going to jump over and we're going to do California Nebula. California Nebula is being lit up by Menkib, which is this bright big star. And it is lighting up the whole thing. So what we're going to do, we're going to go to, oh, this is sometimes quite annoying. All right, let's do this. Let's slew to that. So going back to here, we're going to go back to 1 minute exposure. Just stack that. So 4 seconds, and you can see star streaks because it's still going. And we're waiting for the little red plus sign to come somewhere in this region. Oh, yes. The telescope was pointed into the western sky. So it's got to go all the way around to point to the eastern sky and come right up to it. And here we go. Back to here. Let's wait for the exposure to be done. It's still moving. One more exposure should do it. And there. Now we have stars. Cool. Plate solve. And I want my deep sky annotation so we can see what are we looking at. All right. California Nebula. Let's center this. I'm going to set the target name as well so we can have it written out. It should jump. That's fine. One more plate solve. So here's Menkib, California Nebula. Now it's got to redo it as well. There we go. So even with a 4-second exposure, you can see there's some haziness here. Anything? Okay. There's something there. But with a 4-second exposure, it's just not much data at all. If I drop this way back down, yeah, there's nothing there. Okay, let's fix that. Again, raw data, not much there. So I'm going to switch it to 60 seconds again. See what happens. In this case, we'll do a live stack. Let's pick it up. Yes, yes, yes. So we'll wait. Okay, 6 seconds. If you have any questions, comments, concerns, you can put it in the chat. And I am reading, and it should be fine. All right, I think the issue with the live stack is we need a couple of frames to make it look good. So I did the imaging, at least I did some imaging yesterday. So let's see if I can get this. So we're looking at yesterday. No, here we go, California Nebula. All right, California Nebula. That's what I got yesterday. This is one raw frame, just one. If we zoom in on it, oh, we got stars. We got a lot of noise. So we can see, all right, that's kind of reddish. It's reddish in there. But over here, there's not as much red. We got some stars. Okay, doesn't look too bad. And this is a stretched histogram too. So if I reset it, yeah, that's all we got. That is the raw data. Most of it is going to be pretty dark. A couple spikes up high, but most of it is pretty dark. And our eyes are not very good at differentiating different shades of gray, which is what we have here. So we do an auto stretch of the histogram so we can at least see something. And I did let's see if I can see one of them. I did a stack, and unfortunately, I was not paying attention to all the frames that I was actually getting. And somewhere in here were some satellite trails. Because when I went in to process them, I saw satellites. All right, here we go. So let's let it do its thing. Do I have my low frequency wave? Okay. Yeah, let's see. All right, so we can already see some nebulosity. It's green in the background. It's fine. Stacking will help with that, just like it did with Pac-Man. And we can always process that out in post. So it's fine. I am not worried about it. Remember, this is just 2 frames. All we did was 2 frames. Right. So we'll do it from here. There we go. That's a little bit better. So what do we see? We see the hydrogen gas that's lit up. Why is it called California Nebula? Because from a certain angle, it looks like the state of California with the characteristic bend around, what is it? Yeah, south of San Francisco, Big Sur, where it bends into the greater Los Angeles area. So it kind of looks like California, so it's called the California Nebula. So we're going through here. Let me see. Do I have... Yeah, let me drop this over here first. I've got stuff going on. Okay. Ooh. Oh boy, that's ugly. I am trying to get... Okay. I have my other workstation, which is not wanting... Okay, here we go. It's very slow for some... Oh, yes. It's very slow for many reasons. I do my processing on my workstation in my office, which happens to be downstairs. So I've tried to remote into it so I can see something there, but it is apparently very, very slow connection. I'm going to have to play with that because I wanted to show off what I have down there. Let's see. See if I can just reset the connection, if that'll help. Kind of, maybe. There we go. All right. So while this is processing, let's take a look at this one. So this is Photoshop in my workstation. This is and the halfway decent processed version of the California. So here's my processed version. This is stacked and nothing else. It's with a little histogram stretch. Let's zoom in. So you can see my stars are not terribly round. Again, this was not my first imaging set, and the temperature cooled down quite a bit. So I had to Well, I just took the images, and then later I did a refocus on the image. All right, got a question. On my camera, do I have a mirrorless lens or an infrared camera? This is a dedicated astronomical camera. This is not anything like a DSLR or mirrorless. It is more like a mirrorless, but it has no screen, it has no buttons, it has a plug for power, it has a output for USB 3, and this one has two inputs for USB 2. Um, but other than that, it's a naked sensor in front, and you actually have to screw this onto your telescope. So with this one, I'll show you a little bit of my processing technique. While we're waiting for the California from today to come up, we can look at the California from last night. So it looks pretty decent, but it's also kind of blah. There's not a whole lot of color. It's just kind of blah. So the very first thing we want to do, get rid of the stars. Why? Stars are bright. Stars are very, very bright. They're white, but they're on the bright side of the histogram. And when we want to do some histogram stretching, we want to be playing with the image, having all that white stuff at the end makes it really difficult to process. And so there are a number of different software packages that let you strip out the stars. Okay. It is actually, like, for example, for mine, I use from RC Astro, it is called Star Exterminator. It gets rid of the stars. Does a pretty good job of it too. And you get a version of your image that's starless. Now you can see the nebula. Now you can actually see the structure of it without having the noise of all the stars around it. So in this case, our cameras are sensitive towards the infrared side. And the reason we do that is this red color from hydrogen is very, very red. And on most DSLRs and mirrorless that you buy, just straight out of the box, they block a lot of that red light. Excuse me. The reason why they do that is that near infrared light, which the sensor is sensitive to, if it's not blocked, it will give a fuzzy appearance to your images. It'll also like skew the colors. I actually have a modified camera that has that hot infrared filter removed. Actually, DSLRs and mirrorless actually have two filters, and mine is basically a naked sensor. So any picture I take during the day is very, very red. It doesn't get much blue, but it gets a whole lot of red because now it's more sensitive to that infrared side. I can actually put an infrared filter on the lens, and then I can take infrared images. So this is blocking out everything but the light that we can't see, which is really cool. The sky is very black. The clouds come out very white. Trees, the leaves on trees are very white. It's really, really cool. And those cameras are modified also so that we can take images of astronomical targets like emission nebula, of hydrogen nebula, with those cameras. If I was going to be taking it with a standard stock DSLR or mirrorless, I may have to take like a 3 or 4 minute exposure. With my modified one, I may get the same results in only 30 seconds. So there's an advantage to doing that modification. In this case, what I've done is use the astronomical camera, Star Exterminator. I've gotten rid of the stars. Now I can see just the structure of the nebula. This is this white streak here, satellite trails. So we had a string of satellites that went through that same spot, and I'm betting it was a string of Starlinks, as we've seen before. And when they're soon released from the rocket, they travel in a long string. And then as time goes on, they separate out into their different orbits. But for several days, they orbit together in just a long string. It's really cool to see at night, especially if you're in really dark skies. You look up and there's like this line of dots going across the sky. And that's a Starlink constellation. That's going out. So I didn't get rid of those images. They're somewhere in my subs, and I just went and stacked them, didn't think anything of it, and was like, okay, fine. So this is, it's just an artifact of the satellites that I didn't get rid of. Fine, whatever. It's there. So I have this red image. I have the structure, the basic structure of the nebula. So what I want to do with it, I want to get rid of the noise. Why? Because there's all this noise. So I have some denoise applications that I use, and I smooth out the noise. I get that. We go from noisy to smooth. If we look at a place here with the nebula, okay, I go from noisy to smooth. And when I do, it helps bring out some of the detail. Now we can see this kind of ridge, this swoop here. And if I turn this on, you can barely see it. There's something there, but I'm going to be able to process it more. So now I can see some of the structure, and I'm not distracted by all the noise. And we can see this bright ridge. We can see this dark nebula here, more dark nebula. Once I do that, I can then process the nebula. Now I can bring out the highlights, and I can tone down the, or make the darks darker, make the lights lighter, and I can bring out some more structure. Now it's much more easy to see. This here, this ridge, becomes much more visible. And then we see additional ridges all through here as well. All the structure becomes much more visible just by playing with levels, just little Photoshop techniques. Once I have this, and once I have this looking like what I want it to look like, then I don't like that one. Like, wait, hold on. No, I thought I preferred that one. Yeah, there we go. This is a different version. So once I have something I like, I can take my stars and I put them back in. I do a neat little thing. And again, this is kind of ugly, but I can also do this. So if I take my background and I'll just duplicate that. Duplicate. Come on. No, don't lock me out again. I don't know why it does that. Come on. Come on. No. All right. Well, that thing's going. Let's see what this does. Okay. So California Nebula, 13 frames stacked. It is not the same thing I was looking at yesterday. This actually shifted toward one side. It's fine. I'm okay with that. Let's zoom in. So we can see some of the same structures. We're looking at, yeah, we were looking at this part. This is, where is it? Where is it? This is that ridge. I think this is the ridge over here. This is, yeah, this is the ridge that we were looking at. There's that little dark spot here. Let's look at it this way. We can do a comparison. So here's the ridge here. Here's the ridge here. So we can see with just 13 images, we're able to see a little bit of structure. It's not a whole lot. We want a lot more. But I think there's like 50 something images that I did, and of 2-minute exposures, not 1-minute exposures. So there's more data that way, and we're able to pick out more details. So how come it doesn't like me? It doesn't like me for some reason. It locked up. All right, we can get out of it. Close it and reconnect. Oops, that's not the way I want it. I want it here. Yeah. So we can see the California Nebula, and it is glowing red. There's not much color there other than red. So we know this is mostly hydrogen nebula. Okay. All right. One more try with this. See if it'll let me do it. Maybe not. There we go. All right. Oops. Once more with feeling. Okay. So I did the same color processing on the background, but I have a little trick I like to do where in Photoshop, I go to the blending options and I come in and I can blend down. I separate out my blacks and then I pull this up, and now I'm getting rid of the darkest colors, but not like a direct cut, but a blend. And that lets me have the stars from my original image, but I'm pulling in like behind it my process nebula. And so I have my stars now, I have my nebula, I can see the whole thing, and it looks good. No. What I'm going to have to do is, yeah, I think I need to have a faster connection coming out of my office. So this is a little bit slower than I like. Great. Okay. At least I know. Better for next time. I have to keep closing this thing down and reconnecting. But we can see. Oh, there it goes. I think. Maybe. Nope, doesn't like it. Well, at least it's going better than it did the previous time I tried to do this, where I had my entire network crash. That was not a fun night. All right. Any questions, comments, concerns? If you have any objects you want me to take a look at. So we're looking at part of the California, one of the edge that I cut off yesterday. But we are still seeing some of the same structure. Here we go. Okay, there we go. So here we go. This is the processed image from the data yesterday. What we're imaging right now is this side over here with a little bit off to the side, not quite centered the way I had it, but we're able to make out. If I do it this way, hey, there we go. That's actually pretty good. That's not bad at all right there. So we can see this structure right here is this structure right through here. This is all this. Nice, this part right there. And yeah, so we're able to get some of this data. That's not half bad. Or wait, hold on. That star is this star. There we go. Yeah. So yeah, we're able to see stuff. Is it the best? No, but we've only done 18 images. It's not a lot. I took over 50 last night to get this instead. So again, longer exposures, more exposures get you better images, and darker skies get you the best images. I will be doing some videos when I get back out to the dark sky side. I will be doing more. I'll be doing more imaging, and I'll be able to do a comparison. Objects that were imaged from my backyard using filters in a city with a lot of light pollution compared to images from a dark sky site with almost no light pollution and not filtering anything. I have to have the filters on the camera because I am blocking out the light from sodium vapor lights, the light from all the street lights, all the house lights, everything going up into the sky. I've got to try to block all that out. So the question, been able to capture images of a satellite, space station, or anything? Yes, I was able to capture an image of the International Space Station going across the face of the sun during the day. However, I had the wrong settings on the camera. I had the wrong settings basically on the solar telescope itself. So my image was too slow to capture anything but a streak. I have not tried Hubble. Hubble is very far away. And you also have to have certain mounts to do it. My mount, I don't think is capable of tracking the International Space Station. Not for speed, but just because of the way it processes signals going to it. There are other mounts that process it live and differently. It's kind of hard to explain exactly, but the signals for my mount are sent 1 second late. There are other mounts which are close to real time, which can track things like satellites. My mount is not set up for that. It was never intended to do that, so I don't think I'll be able to do that. I have been waiting for a opportunity to image uh, the International Space Station, and let's see if I can find it. There it is. Um, there's a website called the International Space Station Transit Finder. Okay, and you put in your location, so I can do select from map. I am not in the middle of the Atlantic because it's 0, 0. And let's say I'm going to go for Fort Worth, drop it right there in the middle. Okay, save and close. And now I can say, all right, well, fine, calculate 80 kilometers out. So Tiangong is the Chinese space station, International Space Station, Tiangong ISS. All right, let's check this guy out. It says Friday. This is January 17th at 5 p.m. Sun close pass. Cool. Show it on the map. All right. So this is where I would need to be. So if I want to see the space station pass in front of the sun on the 17th at just before 5 p.m., I've got to be within this band. So I could be over here in downtown Dallas. I could be, oh, hey, here in Mansfield. So cool. I can just drive over to Mansfield. I can do it there. So when is the 17th? 17th is a Friday. Okay. All right. So that Friday, I could be set up in Mansfield. Yeah. Let's see where. Okay. Well, yep. I could be set up in Mansfield. And along this line would be closer to the center. This will be closer to either edge. Wow, man, like down to Midlothian almost. Or I can be down in Cleburne. I can go to Keene. I can do it at Keene. Oh, that might be something. Here's Alvarado. Where is Keene? Here's Keene. So we could do it from Keene. We have the Thompson Observatory at the Southwestern Adventist University in Keene. Is kind of a partner of our clubs. We do some star parties down there. We help them out. They do their own star parties as well. They have a 10-inch TMB refractor in a dome. They have a very nice Celestron 14-inch, the larger big brother of the one I have, in a roll-off, as well as a number of other telescopes. Our club actually has a 17-inch Ritchie Chrétien that was donated to our club in their roll-off observatory until we have ours built in our dark sky site. So that could be feasible. On that Friday, assuming the weather is good, I can go ahead and let them know, hey, there will be an IS transit. We can go down there, set up a solar scope, and do the image, do the recording, and then do the processing. And this time I know what I need to do for my timing, and we can image the space station crossing the face of the sun, which is pretty cool. You get to see the sun with sunspots in the background, and then you get to see the silhouette of the space station. So yeah, they may be feasible. I keep checking every once in a while, but it's not in the forefront of my mind. Maybe this year it should be. So let's go ahead and see what happens when I do this. So I had the same issue. I think this is just extra, I'm not sure if it's extra gas or what around it. But yes, that looks quite ugly. That's okay. But now we're getting some decent data. And the longer this goes on, the better the data. Okay. Any other targets? Come on, somebody give me a target, something in the night sky. Because otherwise, I think this is probably good enough. 25 minutes. I will do stop the live stack. Then we're back to base data. Let's see, what else can we look at? So we're looking at over here the California Nebula. let's just jump over and we can do the Pleiades. So the Pleiades is the seven sisters, and the seven sisters are uh, seven sisters that the god Zeus was infatuated with and started chasing them. And in order to escape, they turned into swans and flew up in the night sky. I think one of the other gods, uh, maybe Hera, I don't remember exactly, turned them into swans and they flew up in the night sky. So there are actually a lot more than seven stars here, but seven is about the limit of what we can see naked eye. I think there are over 200 in this cluster. And in this image, you can see reflection nebula. So the bluish haze all around it is dust. So these stars moved out of their birth nebula a long time ago. And they're moving through the galaxy. And this cluster of stars is spreading out. So they're spreading out in one direction, but that direction is parallel to us. So the stars appear not spread out this way to us, but this way. So an elongation. And the cool thing is, in our eyes, it's together. But some of these stars are moving through a rather dusty part of our galaxy. And when they do, the light from those stars is just reflecting off the dust, and we can see that. I don't know how much we'll be able to see here. So let's do a plate solve. Make sure we're pointing at the right thing. Cool. So we're pointed at roughly the right area. So let's do a live stack again. 1 minute. Yes, yes. Starting a new stack. Excellent. So I think the first image is not going to be great, but I can clear it. If it's all streaky, we'll just clear it and then get the next image. Go. Okay, cool. No streaks. So we'll let this thing go. And in the meantime, let's go back here. So we're seeing this, or we will be seeing this haziness. I hope we'll be able to see some of it. Not 100% sure, but we will see. Boy, let's see. Okay. The filter that I have on here, it blocks out the light from... I know. I will be with you. The filter that I have on here is called dual band filter. It tries to block all light except for the red light that's emitted by hydrogen and the blue-green light that's emitted by oxygen. Also, there's this. We typically do 3 different colors. There's the light from hydrogen gas, hydrogen alpha, what we call it. We have the light from sulfur 2 and from oxygen 3. Problem is, to our eyes, the light from hydrogen and the light from sulfur is very, very similar. It is just a slightly different shade of red. So this filter has hydrogen and sulfur together and oxygen separate. So it doesn't really pick out light very well from reflection nebula like this. I've tried it from the house. It was okay. It wasn't great, but we'll see. We'll see what happens. All right, we've taken 2 images. That's not much. Let's see what happens if there's anything to see. And I'm going to get rid of the deep sky annotation just so we're not bothered by it. Again, let's go. There we go. Yeah, there's a little bit there. Blue stuff, that would be the reflection nebula. And it just looks like noise. Doesn't look like very much right now. But again, we're not really doing anything Yeah, we're right now we're kind of waiting for more data to come in. But here we go. We have the Seven Sisters right in the middle. If I do on, oh, okay, close enough to the middle. I guess I should have recentered, but we'll be able to see at least something through here. We just need more time. And I don't think I have a. Do I have a Pleiades? I may. Let's see if I have a processed image. I know I processed it before. Um, let's see. I'm going to bring it up on the other machine. Where is it? Let's see. Targets. And M45 is what I want. M45. I don't see M42, M45. There, M45. Okay. No, that's not what I want. So I have a lot of data I also use from iTelescope. Um, I have a subscription there, so I'm able to image from there, and we will be doing that in the future as well. And I know I had M45 here somewhere. I just don't see it. Interesting. Annoying. Very, very annoying. No, that will not be it. Okay. We're waiting for this thing to come in. How many? 5 images? So let's see. Yeah, that's an ugly color, isn't it? Green star. Ah, there we go. Now we're getting a little bit more. All right. It's greenish, but whatever. Not worried. There we go. So you can see we have regular stars that don't have much blue around them, much glow. And then we have some of the that reflection nebula around them. You can see there's a little bitty string coming out here. And over here we have more, so you can actually see some of these details. It's starting to come in. Cool. We have more of the reflection nebula up here. We have some darker patches, some brighter patches. The round bit around it, that is basically it's an internal reflection in the telescope. These stars are just so bright that they cause it. The streaks that are coming out, these are diffraction spikes because, well, I have these cables that are hanging out the front of the telescope, and light is actually bending around those cables, and it's a quantum mechanical effect, and it is causing these diffraction spikes that come off the stars. If you look at stars from Hubble, you can see the cross pattern on the really bright stars. That's because there is a cross-shaped spider that's holding up the secondary mirror in Hubble. So it causes those cross shapes around all the stars. If you look at James Webb, it actually has 6 diffraction spikes because instead of having a cross holding the central assembly, it has a tripod. So the spikes are doubled on the opposite side of where they are. So if I have one stalk coming out, I'll have a horizontal diffraction spike on my images. It's just a quantum mechanical effect. But if you know how to use it right, especially for things like Hubble images, it can make your images more pleasing to our human sensibilities. We think they just look nicer, or more of what a star should look like. So we are getting dark areas, we're getting bright areas. So this isn't that bad. So all the stuff around here, that's my fault. It's just my pre-processing. It's fine. I'm not terribly worried. It's just not ideal to what I want, but I did want to see the nebulosity from here. Let's give it just a few more minutes so we can get a little bit more nebulosity. And in the meantime, I will see what I can find on here. I know I had it. I just don't know where I put it. Maybe if I just search for it. Yeah, let's see if I can just search for it. So, M45. Okay. That's not what I want. That's the M45, but that's still not what I want. Astro. Okay. All right, I'm seeing my stuff now. I have to find the version that I want. There we go. That'll do. Okay, so while that is coming in, here is a stack that I did with data from my telescope. This is from a telescope. It's a similar, actually slightly wider field, but this is from data from a dark sky site. So this is pretty good data, but also dark sky. So I don't have to worry about light pollution. I don't have to worry about subtracting the light pollution from my image. This is what I get with really good data. So here we can see all these streaks. So what are we looking at? What orientation we have? Looks kind of like the Big Dipper. It's upside down. So on here we see the Big Dipper, and here's the tail. So this is reversed. Can I flip it around? I don't know. Share, that's not what I want. It's fine. Yeah, so I can see. Here we go. Okay. So there's the tail. So this that we're looking at here is this whorl over here. So we can see a little dark patch right there. And that dark patch corresponds to this area right here. So we can do this imaging from a city. We can see the same thing that a much larger telescope, more expensive telescope in a dark sky can see. It just takes us a lot more processing to do, and it's not going to be as good. But these things are actually in the sky. We can see these things, and it's not that I have any specialized equipment that only I have. This is all consumer grade stuff. Anyone can go buy this, set up an observatory in their own backyard, and start imaging. And I have to say, there are people who don't think that space is real. There are people who think the Earth is flat. It is not. The Earth is an oblate spheroid, and space is very, very much real. There are people who think that the stars are lights in the sky. They don't know what they are, but they say they're, I believe the term is luminaries that they like to use. And they're not. We can not only image the stars. I don't have it here. It is downstairs. It is a nifty little filter called a spectroscopy filter. It's a diffraction grating. It lets me take the light from a star and separate it out into a spectrum. Then I can image that spectrum, drop that into an analysis program that checks the levels of all the pixels in that spectrum, and it gives me basically a graph of the light. Which frequencies are stronger, which are weaker, and from that now I can tell what elements are in a star's atmosphere. And I can also tell what elements are in between that star and us. If there's a gas cloud in between that has certain elements, I can see these drop-offs in the graph. I can see those drop-offs as well for the elements that are in the atmosphere of the star. And by analyzing that, we can tell what the classification of the star is. So there's a whole lot of data that we can get because these things are actually real. It's not an illusion that's put up above us to trick us. These are actual objects, and we've actually sent probes to Mars. We've sent people to the moon. The joke is that NASA went to Stanley Kubrick and said, "We need you to fake the moon landing." And Stanley Kubrick looked at it and said, "All right, I can do this, but we're going to have to film on location." And well, that's essentially what they did. And people say that no one ever went to the moon. I actually have um, two different meteorites from the moon. And the way we can tell that they're meteorites from the moon is because they contain minerals that don't form or that can't form in a water-based environment like on Earth. And we were able to match them with the rocks that Apollo brought back, and they are essentially the same sort of rocks. So again, this is what science is. We're testing it. Science is not a necessarily, well, it's not a philosophy. It's a methodology. This is how we figure things out. We ask questions. We create a hypothesis. We test that hypothesis until it breaks. And we come up with a new hypothesis. And we keep going until we have a set of hypotheses that fit the facts that we have. And from there, we develop a theorem that explains how those facts come together. A law is not higher than a theory. A law is just a mathematical formula that describes something. The highest form of truth that we have in science is a theory. So, when people say it's just a theory, that's a compliment, because it's not just a theory, it is quite at a high level. So, all right, anyway, that was my rant. So we're looking at Pleiades again, and we've got 15 stacked images. Let's zoom in on that star right here. So we are able to see, yeah, we got rid of some of the noise. It's looking better. We can see this darker streak. Let's bring up my image again, and here we go. This is what we're seeing, a different orientation. So this dark patch right here corresponds with this dark patch right there. So if we swing over to the star just on this side, we're going to be able to see something. Not really. Well, we have some streaks this way. I see a streak here, a streak here, probably. So compare it to this one. There we go. Hey, streak right here and a streak right here. So that's pretty good. So we have that streak going through two stars, and we can actually see it. There's this streak right here that's going through these two stars. And if I come back with my image, that corresponds to this streak. Can you see that one? No, maybe not. There we go. This streak, which goes through these two stars. So here we go. So this corresponds with this. Science. I think that's pretty cool. So questions, comments, concerns. If you have any objects you want me to see, let's go ahead and do it. It is 9 o'clock right now. I think we probably go to about 10 o'clock or so. Maybe a little bit longer. It depends on if my kid goes to sleep, which I doubt. It's not a school night, and he is not tired because he woke up really, really late today. So in fact, I woke him up. All right, let's go on. So we have Pleiades. I'm going to stop live stack. And we go back to the basics. So here are those stars, super bright stars. All right, let's zoom out of here. And this time, let's see. It is, let's see, this Fornax. And I want to go to, the south. Let's not go that far. Ah, here we go. We're going to go to Orion. The Great Orion Nebula, M42. So we're going to look at the Horsehead and Orion Nebula, and we'll finish off with those. So let's go. Let's slew right to there. Same section of the sky, roughly. So it won't take too long to get there. This is in the eastern part of the sky. So right now, if we look, southeast, I should say. Yep, toward the southeast. So here's Orion. We have the belt of Orion, Rigel, big, bright blue star. It will die very young. And then we have Betelgeuse, which is a red supergiant, which will die soon. It may have already exploded. in a supernova? We don't know. It is about 5,000 light years away. No, sorry, 492 light years away. Oh, that's not very far. I thought it was further. Oof. So it could have already exploded, and we wouldn't know for more than 400 years. The time it takes the light to get to us. So, all right. Then we have the three belt stars and the Orion Nebula. So let's go here. Hey, cool. It's already coming up. We took one image. However, we need to go ahead and, oops, do a plate solve. I'm going to cut this down to 4 seconds because I want to take a really, really fast exposure to show what it is here. Tools, go back to deep sky annotation. And I really love this feature about SharpCat Pro and a lot of other applications now is you can do the plate solve, see what you're pointed at, and the annotation puts an overlay on your image so you can see, oh, well, this is the star I'm looking at, or that's the star I'm looking at. And I can say Great Orion Nebula right here. I want to center that. Yes, I want to center it. And so what I'm doing is I'm sending a signal to the mount through the application. The application knows, okay, I am this far away. This is my pixel scale. This is how much the mount needs to move. It sends a signal to the mount moves. I don't have to do anything else. This is so much nicer than the olden days. All right. Olden days. Olden days weren't very long ago. Okay, let's do this. Let's zoom in because I want to make sure my focus is good. Is my focus good? Not terribly. All right. Yeah, let's sharpen this up just a little bit more. So I want to do a much faster focus or a much faster image. So I'm going to do 1/4 of a second. So even a 4-second exposure, I'm getting some pretty good images out of it. So here we go. Let's get this. All right. So I'm going to go, if I remember how much this should be, nope, 1,000 down. All right. Let's see, a little bit smaller, maybe not. Oh, fine. This is the boring bit. This is always the boring bit. Refocusing. Getting a new image in. Yeah, I don't think it's going to work. Let's see. And I'm just doing a gross focus. I don't want to go through the whole routine on refocusing, doing the automatic refocusing. This is going to be good enough for us. No, it's bad. Yeah, it's gotten bigger. Okay, how about this? 2.7, 127, not 2,000. The number right here is the position of the focuser. So it's a little motor on the back of the telescope that's connected to the manual focuser, and every one of those is a tick. It's a very, very small movement, but there's a sensor in there so it knows exactly how many ticks have, or what tick it's on, and how far it needs to go to get more. Do I need to go higher? I don't think I need to go higher. Fine. This is probably the wrong direction. Pretty sure it's the wrong direction. Let's see how much bigger it is compared to that. Okay. That's smaller. Okay. Yeah, let's keep it with this. All right. What are we looking at? We are looking at the core of the Orion Nebula. Geez. Let's do a slightly longer exposure than 1/4 of a second. While this is a big telescope, these are fairly dim stars. We'll do a 2-second exposure. That gives us a little bit more data. There we go. So right here in the middle. All right, let's just give it 8 seconds. 8 seconds raw. So we'll get a couple stars. 1, 2, 3, 4. There we go. 1, 2, 3, 4. So here is we call it the trapezium. When you see this through a telescope, like even like an 8-inch telescope, 8-inch Dobsonian, if you start looking at bigger telescopes, 10-inch, 12-inch, and you look through the eyepiece at the core of the Milky Way, you'll see this little grayish cloud around it, but you'll be able to see the stars in the middle. And that is the center of the star forming region. So there are a lot of stars there. I think there are several hundred that we know of now, but the trapezium is what we can see with our telescopes, with eyepieces, and it's just a really, really pretty thing to see because they're stars. You can easily see them even with light pollution of the city. It's just really, really cool to see. So that is actually a star right there too. So we have the 4 stars of the trapezium. Let's see if there are 6. Some of these are doubles. It's hard to see with this one, especially with this focal length. But if I fix the histogram, let's blow this thing out, we can still barely make those out. Barely. But they are right there. But we can begin to see the nebulosity. We can see more stars, especially if I zoom out now. We can see the color. So we can see the hydrogen here. We can see the dust that's blocking the light from behind. We can see this star lighting up this region of hydrogen and this dark band, which is attached to this complex, blocking the light from behind. There are some reflection nebulae in here that are really hard to see because this is only an 8-second exposure. But we'll do a 1-minute exposure. 60 seconds. And let's do the live stack. So there we go. We have the trapezium right there in the middle, with a little bit of the brightest nebulosity around. You can see a little bit of detail. The light levels are not all consistent, which is fine. We can even make out some red even with a short 8-second exposure. And of course, by stretching the histogram. But we got 1, 2, 3, 4, the 4 main stars of the trapezium. And let's give it a couple more seconds and see how much pops up. So I was imaging yesterday. Where is it? There it is. Let's see, where was it? There it goes. So I was imaging this yesterday as well, and let's fix that histogram. That's still not right. Okay. The core is going to be blown out. Let's give it some more time. This needs to process. It's got to cook. So we've done 1 frame stacked. That's not nearly enough. We need more data. So this will get cleaned up. In the meantime, this is what I imaged yesterday. Now, it's the exact same thing. If I drop it down here, it's the same thing. However, a few more images. I think I want to say I just did 12 after I did the refocus, but we can see this star and this star, or this star and these 2 stars, this star and those 2 stars. We have the core. We have the complex down here. And then we have the Running Man Nebula. Barely the beginnings of the Running Man Nebula right here. This application is called Astropixel Processor. There's a number of applications that we can use to process our images. Excuse me, I said to sneeze. At the top end, we have PixInsight. Fantastic, very, very powerful program. Very, very steep learning curve. But PixInsight is the application that pretty much everybody uses for their high-end processing, including NASA. The images from Hubble, the images from James Webb, they use PixInsight. They have some custom plugins that they've used uh, for their data, but it's still pretty much it's the same software that we use. It's the same process flow that other astrophotographers use. I like AstroPixel Processor because it is very, very simple. It is very, very fast, and I can at least get something out there very quickly and then do PixInsight later and process it, get more extensive processing, do things like pixel math, which is pretty cool. Um, but this is like a quick way of doing it. And honestly, I can go from uh, image data to a complete picture. Depending on how quickly I want to do it, I can get it in about an hour. Or if I want to really get into it, I really want to play with it. I can get a form where I can start to do that in about 3 to 4 hours, especially if I have a large number of exposures and I want to do some tricks to pull out a little bit more detail from there. There's some really neat tricks to do it. So I'll get into those later at another time. Um, it's really esoteric, but it's cool stuff that you can use. So on here, yeah, my stars aren't quite round. They're a little bit streaked. I didn't have very many exposures. My data is not very clean. There's still a lot of noise in here, but we're able to see more. We're able to see the star here, and where we had that nice little bubble of glowing hydrogen, we can see a lot more detail now of this dark nebula that's blocking out the light from behind. And if we jump over, oh, nope, this is what I want here. So let's see. Well, still ain't pretty. It's getting there. Let's see. What about this one? There we go. Okay. So this is 5 images, 1 minute exposures. Those things I think were 2 minute exposures from last night. Let's zoom in. A lot of noise. But hey, we can see that same complex. Right, here we go. Oops. Try it again. There we go. Okay. Yeah, so we can see the same complex. So we have it's the same thing. And the neat thing about this is because I haven't moved my telescope at all. I haven't moved the camera. I haven't done anything. It's the same place where it was last night. The orientation is exactly the same. So we can look on it. Here's the star. Here's the star. We have this complex with a little bitty finger of dark nebula going towards the star. We have that same little finger here. There's this little patch of darkness there. We have a patch of darkness right here. There's a patch of darkness right there. We can see it right there. This is just the cleaned up, stacked version with a lot more data than what we see here. That's it. And I haven't done any noise reduction. I haven't done any additional processing. This is just a stretched histogram, and that's essentially it. But you can already see data in here and compare it. So we have these streaks going through here, these paths that we can see. This one next to this star, we have one here and one here. So we can see that same dark area here and here. We have this kind of wave over here, and we can see the wave over here. And again, this is live data. What we're seeing on top is live data. It's a 1 minute exposure. I'm getting it now. What I have here is data from last night that's already been processed. But it's the same thing. We can see it's the same thing day in, day out. And if someone else starts imaging the same thing, they don't even have to have the same camera that I do. They don't have to have the same telescope I do. They don't have the same, they don't need to even be at the same location that I'm at. They can image it too in a completely different orientation, and we can flip it around in Photoshop. We can match it up, and we'll see the same details over and over and over. This is how we know that this stuff is real. It's not something that's painted on a dome. it's not an illusion on there. People are looking at it from different parts of the globe, seeing the same thing over and over and over and over. And we can go back 10, 20, 30 years, look at older images, and we can see the exact same structures. Because they're so huge, they change over very long periods of time, thousands of years, tens of thousands of years. So something from 5 years ago, 6 years ago, for a lot of times, something like this, they're not um, they're not changing that fast. All right, I have okay. I have a question. What is the closest nebula? I don't remember. I'm wondering if it is the Orion. Hey, that's what we have Google for, isn't it? Let's see. Closest nebula to Earth is the Helix Nebula. Do I have the Helix Nebula? Yes, I do. Let me see if I can find it. So the Helix, let's see, M45, we did that one. Helix. The Helix is a planetary nebula. And it is, well, let's see. Let's find it on here. When did I just imaged it not too long ago. Yeah, here's the Helix. Ooh, best time. This is going to be toward the south, and it's a planetary. And so it has the blue of oxygen, and it has the red of hydrogen, and right in the middle is a bright white dwarf, which is lighting up the whole thing. And Hubble's got some really good images of it. Where is it? Yeah, so it's under the moon right now, which makes it hard to see. Helix. Yeah, I just imaged this thing. Did I do anything with it? Did I process it? I didn't even process it. Yeah, I did this. Yeah, I did it not long ago. Oh, come on now. Now I have to figure out which of these images are actually viewable. How big is this one? Let's see. I have it on a different one. Yeah, there we go. Yeah, this is one of my, yeah, this is my Helix. Okay, so, yeah, that's my Helix from last year? I want to say it was last year. Yeah, so, I think so. I don't remember exactly. But anyway, yeah, that's what the Helix Nebula looks like. It is more of a summer constellation, or at least the autumn constellation, because in winter now it is way further into the western sky and sets rather early. So something you want in the summer, late summer, and fall in order to see it. But came out pretty halfway decent. Yeah, but that is the closest nebula. I have to be careful because, yeah, I need to speed up my network to make it look much better, make it work much better for me. In the meantime, I have to reconnect. All right, let's do that again. Okay, so I want to get back to Ryan. Let's look at the Running Man Nebula down here. Here we go. So this is the Running Man, and it's called the Running Man because it kind of looks like a man who's running. Kind of. It's like, here's the head, here are the arms, torso, and the legs. So this guy's upside down. but it comes like a stylized figure of a man running. It was only recently, I think not too long ago, sometime in the last like maybe 20 or 30 years, that it was named the Running Man Nebula. It was, yeah, it was relatively recent. It didn't really have a name other than its catalog designation. So we can see this dark area right there. And if I bring this down, hey, there we go. So we have the dark nebula right there, dark nebula right there. Same image. This one's live. This one's just getting stacked right now. I'm not inputting anything. We're just getting what's there. And you could see I was able to slew to the Orion Nebula, but it wasn't centered, so I had to recenter it. If I was faking it, it would, I mean, the obvious thing would do is to have it exactly the orientation you're expecting and get to it every single time absolutely perfectly. And the first image that comes up, it's always going to be a perfect image, what you expect to see from an image of space. Oops, let's see. Nope, let's log in again. This is my monitoring, laptop. And it locked me out, so I'm going to put it right back in. Okay, so we're getting live data. We're processing live data. We're doing a live stack. So what I have here, it is 14 images from 14 minutes that have been stacked to get this, but otherwise not processed at all. And then this image, which I took last night, of the exact same object and the exact same orientation, which is, I think, I don't remember how many images I did. These are 2-minute exposures. Let's see. Let's find out. Load. How many do I have? Lights. So I have 17, 18. So I used 18 images and stacked them to get this image. So it took 18 to get to this point. And if I turn off the stretch, guess it's not going to do it. Oh well. Okay. So I'm getting real data. This is processed data. This is live data. If I just grab it over here, pull it back down. Yep, we're getting more. Oh, cool. Satellite. Let's see. Yep, that streak right there, satellite trail. See, you can't really see it that well. Let's set it 50%. Yeah, satellite trail. Right through there. I mean, it happens. So it happened with my California Nebula at a, oh, there, see, it continues through. So in one of these last exposures, I had that. Now, when we stack, we average the data. So if it's one satellite and you have 100 pictures, kind of average that satellite trail out. But I only had 18. So, well, never mind. On here, I only have 16. And so the satellite trail has not been averaged out. It is what it is. I'm not worried about satellite trails right now. We're just having fun. But you are able to see satellites. The polar scope that I use, it's called a pole master. It points at the North Celestial Pole and helps me align my mount so it tracks properly. Every single time I use it, I will see satellites on polar orbits crossing near the celestial North Pole. Every single time. When I was doing my alignment yesterday, I saw 2 at the same time. So with a good pair of binoculars in dark skies, with a telescope, you can see satellites. In fact, if you have a decent sized telescope with a wide enough lens, as you're observing, you can see a satellite crossing your field of view. If you catch it fast enough, you grab the front of your telescope and just follow it around. And you can keep following it until it passes into the shadow of the Earth, and then it suddenly disappears. You can see it with the International Space Station at just the right time, where if you use there is an application, let's see, what's it called? It is ISS, what is it called? ISS on Live. And I want to say it's a NASA application, but I'm not 100% positive. But it has NASA TV on there. It also has a nice little map of where it is right now. I guess I can put it up like this. Oh, let's do it that way. Here we go. So it shows where the space station is right now. You know what? Let's just do it this way. Here we go. So it shows where the space station is right now. And that circle around it is the area on the Earth where it is visible, where it's above the horizon. Again, oblate spheroid, Earth is not flat. If this goes over your area at certain times, specifically evening and morning, you can see the sunlight reflected off of it, even though it is dark around you. So it is a neat little application, and I use it, and I think it's a lot of fun because you can go outside, you can see the space station, and if you have very nosy neighbors, you look at your phone and you put up to your ear and you watch it, and you just look up like this and you point up at it. You point up at the space station while you got your phone this way, and you make sure all your neighbors can see you, and then they start looking up. What are you looking at? Well, you're looking at the space station. You go as loud as you can. Yeah, I can see you. Yep, looking good. Okay, can you see us down here? Yep. Okay, all right, cool. We'll see you next pass. And then your neighbors think you're crazy, which may not be inaccurate, but nonetheless. Oh, I guess I should have done that. So, yeah, I had it on the little bitty camera. May have been small to see. So what are we looking at? We're looking at Orion Nebula. Cool. Okay, it is 9:34. We've done 20 images. This looks pretty decent. We get more data. I'm going to zoom in 100% on here because I want to focus down here. I want to see what we're imaging, compare it to what I pulled in last night again. So here we are. What do we have? This star corresponds to this star. This star corresponds to that star. Do it this way. So we have this dark nebula is this dark nebula. We have a little finger here, little complex bump coming out here. Same complex bump. We have that little bitty dark spot, that dark spot. We have a darker spot here, darker spot here, dark there, dark there. Bright patch, red, lighter red, white, red, lighter red, white. The data's there. Everything matches up. So this is all working. To me, this is just really, really cool stuff. Okay, what else are we looking at? Okay, let's do the horse head. Do the horse head next. I didn't even process the horse head from last night either, so I'm not going to worry about it. Instead, we'll do the live stack. Okay, wait, one more image. Only 7-8 seconds. That's fine. And then we'll kill the live stack. Horse head is very, very close by. We'll do the horse head in flame, and then I think we can call it a night. It's not terribly late, but honestly, I have to make sure my kid goes to bed. And there we go. So let's go ahead and stop the live stack. All right. We can see one last image. Again, this is a single exposure, a single frame. We're seeing the trapezium in the middle. We're not seeing a whole lot of data from what we just saw. We need more exposures, ideally longer exposures, in order to see what we want to see. And this is the fundamental bit about astrophotography is one picture ain't enough. and you just need more and more and more. Okay, I need to do home to now. There we go. So this is pointed at Orion. Turns my labels off. I don't like that, but that's fine. Here's the Horsehead. The Horsehead is a hydrogen emission nebula as well. Well, technically, this is the hydrogen emission nebula. The head itself is, salute to that one, is a dark nebula that's blocking out the light from behind. Now, what's really interesting is if we image this in infrared with, say, James Webb, we can see stars through the darkness of the Horsehead Nebula. Hello. Why is it not slewing? Where is it? There it goes. That's not what I wanted. Fine. Slew to that. It's slewing to the center of a much larger complex. So when we look at Orion, we just see the belt stars, we see the Orion Nebula, we see the Horsehead and the Flame. There's actually an entire molecular cloud complex. There's actually a ring around the Orion Nebula of hydrogen gas. There's a whole lot of nebula in there. There's a lot of gas and dust. It is a massive complex. It is not just the Orion Nebula or the Horsehead or the Flame. Those are the brighter nebula that we can see, but it ain't all. So we're going to do the same thing we did last time. We're going to cut this down to 4 seconds and do a plate solve and the deep sky annotation. So we have Flame and the Horsehead. Where's the Horsehead? We'll do this. Let's just center that in view. Okay, so cool. Got that. And again, the raw image, we don't see very much because everything in the histogram is way off to here. Okay, so we have some stars and that's it. Let's stretch the histogram as much as we can. I can barely see the flame right there. So obviously a 4-second exposure is not enough. Let's go to 60 seconds. All right. Time is it? We've got 9:39, so we can get some more images in here. Start live stacking right away. Ah. Horrible, ugly, ugly. But that's fine. That's the old image. New stack of Horsehead Nebula. So we got 30 seconds left. All right. In the meantime, I'm going to see if I can find my Horsehead somewhere. Again, it's called a horsehead because it looks like a horse's head from certain angles. No, that's not what I need. I need that. Now horsehead. Okay, here we go. But that's old. Oh, hey, cool. What do we see? We see the flame and we see the horsehead. Is it ugly? Yeah. Because it's literally one image. But we can already see the horse's head, the neck, and the head part. I mean, it doesn't actually look like a real horse's head, but maybe a seahorse. Kind of looks like a seahorse. We just need more data. It's super noisy. We can make out some shapes, but there's just so much noise to this. So instead, let's see, is it on there? What did I do? I have images from years ago, which aren't very good. This one is, okay, no, got slightly better. It'll get better. Okay, I have lots of data. So let's see, what this one? This one's from February. Let's see. Got another screen that I'm looking at. Yep. But I have issues with speed down to my workstation, my office. To wait for it to load. Okay, so we're at 3 images in just a moment, and stacking the third image, and it gets a little bit better. And every single time, it'll get a little bit better, a little bit better, a little bit better. There we go. All right, now we have more of a shape. Color still looks, well, let's be honest, it looks awful. If I do it that way, nope. Okay, they're a little bit better. So we can see the horse's head right there, the brighter nebula in the background, and we see the flame. The flame is typically visualized more yellowish. This is mostly hydrogen alpha, and this is hydrogen beta. They're two, again, slightly different colors, different shades of red. They're just two different frequencies. So we can image them separately by using different filters, but there are also filters that take the band that includes both of them. I'm trying to bring up one of my images of the horse head, and it's just very, very slow. Yeah, I think my office is actually directly below me, but I don't have an easy way of dropping a cable directly down. I might have to put a hole in the wall. 2 holes in the wall. Yeah, and drill through a joist. Hopefully not. I'll always figure that out later. But my horse head is just not coming up. Let me give it a moment. Reconnect. Okay, so we have a bright bit right there. That star. That star is on the attack. And a lot of stars have al as the first 2 letters, al, because they're Arabic. During the Islamic Renaissance, I think that's what it was called, or there was the Islamic scientific age that Baghdad and a lot of other several other cities were centers of learning, and astronomy was a really big deal. But this is before they had telescopes, so everything was literally just the eyeball Mark 1. And but stars were cataloged and stars were named. So yeah, if you're the first person to name a star and you write it down and other people accept your naming, great. Okay. Yeah, I don't think we'll see the horse head process. This is just taking way too long, and it's not working the way I want it to work. That's okay. So the horse head is actually very close to the Orion Nebula. It's just literally a hop, skip, and a jump away. So this is actually some gas. There's another little nebula right there. Let's see if we can find. Is it on here? Yeah, there we go. Little reflection nebula right here. Reflection nebula right here. So if we look back, so reflection, reflection, a little bit of reflection, should be, yeah, reflection right there too. So while we're looking here, here's emission, or what looks like emission so far. Bright. Not what I wanted. It's somewhat. Yeah, it's okay. That's actually a little bit better. It's still not pretty. It's only 7 images. A lot of banding. I really don't like the way this does the live stack. It's not the same as processing, um, but we're able to see it. So we're able to see. Oops, too much. We're able to come in. We're able to see the horse head right there. It's noisy, but we can make it out. We know that something is there. We can see the stars. We can make out the color in the stars. And I wish. Well, okay. Hang on a bit. Uh, Let me do something. I'm going to see if I can find it very, very quickly. So, while this is still coming in, Barbara Wilson's Ain't No List. The Ain't No List was a list of 100 objects which don't exist.
Good night.
You're going to sleep?
Yeah.
Good night. Say good night, everybody.
Good night.
So heavy. Dobranoc. Kocham. So the Ain't No 100 list was or is a list of 100 objects that don't exist. Things like sunspots on Rigel, which they do. They're technically things that we can't observe from Earth. So, sunspots on Rigel, Venera 7 on Venus, the spokes in the Cartwheel Galaxy, the rings of Uranus, seeing it with a telescope. Like, these are all considered naked eye observations. And one of them is number 46, any galaxy within 1 degree of the Horsehead. Turns out there is a galaxy within 1 degree of the Horsehead. I actually have an image of it somewhere. Now I gotta go find it. I even saved it somewhere. I gotta see where is it? Where it is. If only, if only, if only. That's the problem. Now I'm gonna hunt this thing down. I don't like hunting stuff down like that. I'd rather have it in my hands. There it is. Found it. Okay. All right. There we go. So while this is going, still coming in. My orientation. Oh, we might actually, it might actually be here. Okay, here we go. This is an image I took years ago. And yeah, here's the galaxy right there. So the horse head is, the orientation is a little bit different. But this is a galaxy. It's a Mac galaxy. It's a Mac catalog, MAC. And I gotta log in again. Okay, so it is a galaxy. You're seeing it through the winter Milky Way, through a nebula, on the other side of our galaxy. It is tiny and it is distant, but I was able to image this with a much smaller telescope. Let's see if we caught it today. I don't know if that's the case, but we'll find out. So let's do this thing. Okay. I'm looking at one monitor, looking at the other monitor so I can match them up. Okay, I'm going to go in 100% magnification. All right, a little bit darker, that's fine. So we're seeing stars. We only have 12 images, so it's going to be noisy. It's fine, I'm not really concerned. I'm looking for is this right here. This is my guidepost. So now I'd be looking across. Okay, I'm gonna look across, and I'm seeing this pattern of stars right here. So this is a double, single, bright, and I have this one. Okay, this one across, I have 1, 2, 3, 1, 2, 3, and then hang on. So I'm looking at up, down, down, and this. That's it right there. That's it right there. This. Okay, that's pretty cool. And if we look at it, it looks a little bit elongated. It could be a little bit elongated in this direction. This right there, that's a Mac galaxy within 1 degree of the Horsehead Nebula. That's not a star. I mean, that's pretty cool, isn't it? I think so. So we've got 13 images, 13 stacked, 1 minute exposures. And with that, we're able to pick up a galaxy within 1 degree of the Horsehead Nebula on Barbara Wilson's Ain't No List, number 46. That's not bad for a Thursday night. Especially not when I'm in the house, nice and warm, when it is quite cold outside. So, yeah, it's nice and chilly outside. My camera sensor is at minus 25 degrees Celsius. It's not bad at all. Not bad at all. Okay, so again, we're looking at a Mac Galaxy, a Mac catalog Galaxy. I have no idea how distant this thing is. I tried to find it. I found the designation for it, but it's one of those, it's a galaxy. It's really far. There are trillions of galaxies. No one's really done an analysis on this thing because it's in so much nebulosity. It doesn't have much detail, and it's just a really, really obscure one that we don't even know how far away it is. So it's just, hey, there's a galaxy there, but that's all we got. Let's see, I'm getting just messages. Yes, very well. Okay. So let's get out. We're looking at 15 minutes of exposure. Let's see if we can make it prettier. Ugh. So this is relatively raw. We're not seeing really anything here. So yeah. So we got the horse head, we've got the flame. The orientation is different. Yeah, here we go. So this is the image that I took years ago. Excuse me. It is pretty noisy. But I was able to take this from a dark sky site, and that's the galaxy right there. That's what we were looking at. Let's see if I can zoom in. Yeah, there we go. So we were looking at these stars, and then that curve of 3, and it's down, and it's right there. So that is, let's see if we can find it again. I always have to have that reference because I can never remember exactly where it is. Here we go. So we have a reflection nebula right here. We have the horse head here, blocking out the light from behind it. And then we're going to go find those two. Zoom out slightly. Okay. Those two stars, compare it to those two stars, go past them to find those two. Up too far. So it's those, then over. Oh, here we go. So it was the right place. So those three, that little curve, and that little blob right there. Not a star, but a galaxy. So we zoom back out, auto, out to here. Somewhere right in there. Kind of hard to see with it zoomed in so far, but there we go. It is a galaxy within a degree of the horse head. I really like to find that one every time I can. It's just a neat little thing to see. We have, here we go. We zoom in again. We have the hydrogen. We have a little reflection nebula here. This is not a nebula. This is just reflections inside of my telescope tube. We have the flame nebula. We have another little emission nebula around this star. I think there was going to be, yeah, there's a little bit of nebulosity here. So there's a little reflection nebula. There's a little arc right there. This is another emission nebula of hydrogen. I believe on the other side, let's see, what do we have on this side? Yeah, a little reflection nebula and a reflection nebula. So there we go. It is 9:58. It is almost 10 o'clock. It's a good time for me to stop. Oh, excuse me. Have to make sure my kid is in bed. But this was a nice little impromptu star party for the Fourth Astronomical Society. What did we get to see today? We saw Pac-Man Nebula. We saw Able 2, a tiny little planetary nebula in the vicinity of the Pac-Man Nebula. We saw the California Nebula. We saw the Pleiades. Then the Orion Nebula. And now the Horsehead, the Flame, and a little bitty Mac galaxy near the Horsehead. So that's not too bad for 2.5 hours of observing. Normally, when I would be doing imaging, I'd be taking a lot of images for a lot longer. I take hours of images. In this case, we're just doing live stacking. We're doing 15, 20, 30 minutes of gathering data per object, doing a live stack so we can see some of this bare minimum processing just to kind of eliminate the noise. You can see a little bit of the data, and personally, I think it's really cool. But my horse head, I want to try one more shot if I can see one of my processed versions of the horse head. I'm kind of annoyed at my slow connection. Yeah, I don't think it's gonna work. If I was downstairs at my desk, that would be something else, but I think I've got something else going on. It's just slow. So I'm not gonna worry about it. It's fine. We've done quite a bit today. So if you have any last minute questions, comments, concerns, you can go ahead and put it in the chat. I don't see anything else going on right now. Stacking is getting better signal to noise ratio. Been doing this for years using software like Deep Sky Stacker. Yes, there's a number of different software packages that you can use. If you are interested in doing something like this for yourself, whatever you do, don't go out and buy a brand new telescope. Don't ever buy a telescope that has pictures on the box. Whatever you see through the telescope will look nothing like those pictures. The telescopes aren't large enough to display a picture like that with color, even if you're looking at Jupiter or Saturn. Those telescopes are typically much smaller, which means you're not going to be able to resolve great details. Everything's going to be fuzzy. They will give you eyepieces that claim to give 1000x magnification. In our atmosphere, on an average decent night of seeing, you won't be able to get more than 200x magnification in any case. Doesn't matter the size of the telescope. You're not really going to be able to get um, usably good magnification above 200. On a really good night, maybe 400 to 500 with the right telescope. If you're in a place like Hawaii on Mauna Kea, you're at 9,000 feet. You have a good, clear, still night, no wind. You're up above a large part of the atmosphere, the thickest part of the atmosphere. You can push higher magnifications. The reasons why we have telescopes, large telescopes, on places like Mauna Kea, places like Chile, um, in the Canary Islands, on mountaintops, up high above the atmosphere, is that the air is much more still. We're not looking through so much thick air. It's much thinner up there, and it doesn't affect the optics as much, so we can get much higher magnifications. And again, they're doing the same thing. They're doing imaging. They're doing multiple minutes of imaging and then stacking and stacking and stacking to get their data. So they're also using things like adaptive optics by shooting a laser up near the thing that you're imaging and analyzing the reflection of that laser off the molecules of the atmosphere. You can use a computer to process that data, and then using little micro servos on the back of your very, very large mirror, flex that mirror just a little bit. And if you flex it just right, you can take the shimmer of the atmosphere out of your image. Really, really cool technique. It's also really expensive, so it's only for those big telescopes. But the computer will in like 30 times a second will flex that mirror just a tiny bit in order to stabilize the image of that laser. When the laser is jumping around, your star is going to jump around. If it locks that laser down to a little bitty round circle, you know that your stars are going to be little bitty round circles as well, so you can get finer and finer details. Essentially more magnification. But we can't do that. So we got to deal with the best we got. And we're getting more data at 24 stacked. We see more nebulosity here. We see finer details here. We see more nebulosity here. We see nebulosity all through here. This is a dark patch here. Remember, this is all the same big complex. So you can see all the stars back here, but very, very few here. So this dark area, this dark nebula, is actually blocking out the light from stars that you would otherwise be able to see. So there's that. Back to buying a telescope. The quick and dirty recommendation we always give is, if you're really, really interested in astronomy, join an astronomy club, join one in your area. Almost all of them have library telescopes that you can check out and borrow. They may have telescopes at their dark sky sites like we do. You can use those scopes without any additional charges other than club membership. You have to go out there and get them or use them. And you can see if you're really interested. If you are, my recommendation is always an 8-inch Dobsonian. An 8-inch Dobsonian is a Newtonian on an Altaz mount. It goes up, it goes down, it goes left, it goes right. An 8-inch is it's a really good sweet spot for telescopes because it's not so big that it's hard to carry. It's not so small that you don't get a whole lot of detail. It gathers a really good amount of light. I like to call it a forever scope because you buy it once, and even if you get bigger scopes, even if you get more expensive scopes, it's still a good scope that you can just pick it up and take it outside and use it within a few minutes. My setup is complicated, and let's see if I have it. Where'd it go? Did I get rid of it? No, here we go. Nope. Where'd I put it? Yeah. My telescope is, it takes a while to set up. Okay. Point blank, it just takes a while to set up. So yeah, here we go. So this is a scope that we're using tonight. It is a 11-inch Schmidt Cassegrain in a normally it's an F10. I have it configured as an F1.9. I haven't even turned on the guide scope, which is this little scope on top, which is doing straight unguided imaging. Honestly, the mount is good enough that it can handle even, I think, up to a 4-minute unguided exposure. We're good. I'm not worried. But this typically, from completely broken down until completely set up, is about a 40-minute job. It takes a while. I do have 8-inch Dobbs as well, and those take only a few minutes to take outside and set up, but they are visual only. So I recommend that 8-inch Dobsonian. It's a really good size. But before you do that, I would say binoculars. If you're going to buy something, buy a good pair of binoculars. They will last you a lifetime if you get a decent pair. I have 10 by 50 Nikons. I bought them 25 years ago, maybe, yeah, about 25 years ago. They are still absolutely fantastic. Still use them. Actually, my kid uses them more. But, past that, if you want to get into astrophotography, I would say start with a DSLR and your lens, whatever you have right now, on a tripod. Do star trails. Learn how to do star trails. You can go online. There are tutorials on how to do star trails. Again, you take multiple images and then you stack them. Learn how to do stacking. There's free software out there. You can get the free software and use those. You don't have to pay for it. And you can learn. Then you can pay for software that does a lot more. After that, get a star tracker. The Sky Adventurer, Skywatcher Star Adventurer has a bunch of different tiers, and like the cheapest ones, you can get them for maybe you can get them used for just over $100, and it basically tracks the stars in the sky. It's just a clock drive with the motor. You attach your camera to it, you point at the section of the sky you want, you set it going, you have it polar aligned, and it will just move very slowly with the sky. You can take longer exposures now with your DSLR. When you upgrade from that, you would go to a small tracking mount and you would get a small telescope. Put your DSLR on the telescope, start imaging that. And once you get good, especially with not just with imaging, but understand the concept of guiding and things like that, and you get into processing, at that point you can get bigger and bigger and bigger. It takes time. Some people can speed run through it in a year or less. It's not that easy. It takes a lot of time to do it right, and to learn the processes. What I'm doing right now, this is the culmination of many years of practice and failing and practice and failing and practice and failing and wasting 5 years on a mount that was broken until I figured out what was wrong and I fixed it. Not this mount, a different mount. And then that mount worked perfectly from then on. But like, I still think, well, I wasted 5 years of going outside at night and trying to figure out, why is this mount not guiding properly? Why am I not getting good images? But anyway, that's in the past. So again, my recommendation is join an astronomy club. It doesn't have to be ours. It can be a local one, especially if you're not in Dallas-Fort Worth. Join the club, go to meetings, listen to what people say, go to their dark sky site, use their equipment. Let's see, I log in yet again. So those are my recommendations. See, Bartosz is here. I'm terribly sorry, but I'm about to shut down. It is after 10 o'clock. It's a little bit later than I expected, and I have to put my kid to bed. He is in bed. I have to make sure he stays in bed. If anyone has a 8-year-old, 9-year-old, 10-year-old, you know exactly what I mean. They tend to escape, and you have to wrangle them back in. So After 32 minutes of imaging with 1 minute exposures and doing the live stacking, we really knocked down our noise level. The image looks a whole lot better. We're able to see some of the detail here in the horse head. Is it perfect? No. Have I done a lot better? Yeah. But this is a relatively short exposure for this object. But we're still able to see it. We're able to see the horse head. We're able to see the flame. So I'm fairly happy with what we were able to do today. Again, it's after 10 o'clock. It's 10:12 right now, Central Standard Time. I have work tomorrow, so do many of us. So I am going to go ahead and sign off. Um, thank you very much. I appreciate everyone who supports our club. Um, and please check out the website. And if you have any questions, comments, or concerns, you can go ahead and send messages through the YouTube channel as well. And I do read them. You can put in comments on the live stream after we're done. And thank you very much, and good night.